Okay, all right. So I know that I kind of went into a lot of technical details, which might have bored people who are still beginners. But for beginners, you need to understand that there's a concept of discretization, which is nothing but creating the mesh and solving the equations. And I can come up with a very simplified PDE, dou u by dou x plus u times dou u by dou t plus u times dou u by dou x equal to 0, right? So this is called as the linear convection PDE. Why? Sorry, that's the nonlinear convection PDE, but I can write the same equation with a constant velocity c in front. And this equation is called as a linear convection PDE. Why? It's called one-dimensional because yes, we have cancelled out all the derivatives. It's called as the convection equation because we have dropped the pressure and diffusion terms. So only convection is remaining. So if I discretize this, this is quite simple. So this is u at u new minus u old divided by delta t. I'm just using my slope formula is equal to minus c times u old at x plus delta x minus u old at x minus at x divided by delta x. So the superscript is basically, so the superscript is the time index and the subscript is the space index. So with this, what I can do is I can say u new at x plus delta x is equal to u x plus delta x, the old value, minus c times delta t by delta x multiplied by whatever we have here. This is a very simple update rule. This is called as time marching. I'm not explaining the details here because that is something that I don't want to do right now. Let me see if I have MATLAB. Oh, unfortunately, I don't have MATLAB in this computer, so I cannot show you a demo. That's fine. That is something that I can show later. So the basic idea is this right here is no longer a partial differential equation. This is actually an algebraic equation. And who is great at solving algebraic equations? Well, your computer is. So you take this equation, you feed it to your computer, it's going to solve it, right? And this is what you call as solving the linear system. And depending upon how you structure your equation, you can get a system of uncoupled simultaneous equation or a system of coupled simultaneous equation. This is what you call as explicit and implicit. And if you do that, your results are going to change, and you'll basically be able to solve the system, which means you'll be able to get the velocity profile. So this is just for linear convection. Similarly, if you have additional equations like like continuity equation, momentum equation, energy equation, you can follow a similar procedure. This procedure is what people call as a solution algorithm. And at the end of the day, you will always end up with a matrix that is called as a linear system. And to solve the matrix, there are several methods. These are called as linear solvers. And when you solve it, you get your answer. Okay. So moving on. Well, how do you do all of this in a software program? Well, here I have a simple software which is called as Converge Cfd, right? This is the company that I worked for, so I'm very comfortable with the software. So with Converge, you can do external flow simulations, internal flow simulations, pretty much anything that you want. So here what I have is I have an airfoil. So if you zoom in here, you can see that I have an airfoil. And what I'm doing is I'm simulating the flow over it. So the first step that I'm doing is I'm creating a box around my airfoil. This is what you call as a virtual wind tunnel. Why virtual? Because you're doing it in a computer. And through this particular phase, right, that I've selected, through this phase, you have your inlet air coming in. And you have an outlet on the other side through which air escapes out. And then on top of the bottom, you have symmetry boundaries. And then at the airfoil, you have a no slip boundary condition. So that's what boundary condition means. For each and every part that you have in your domain, you need to provide the boundary conditions, because at the end, you're solving partial differential equations, which require boundary conditions, correct? So when you do this, what you can do is you can use this information. Let me just